So since we are talking about energy, and we will be talking about energetics and metabolism and enzymes and enzymatic reactions and all of that, I need to introduce the concept of what is a spontaneous reaction versus a non-spontaneous reaction. The first thing I need to tell you is that there's different types of molecules, there's different types of structure. It's not just about molecules, but different types of physical structures. And some of those structures are either in a high level of order or at the low level of order. They are either organized or disorganized. Now, without going too much into the details of thermodynamics, because this is way beyond what we need to know for this presentation and even this course, I need to explain something that is fundamental to energetics. And here it is. There is a law, it's called the second law of thermodynamics. And it says this: the universe has a tendency to go from ordered to a disorder. And disorder has the concept of disorder has a name. And that name is called entropy. It's called entropy. So the universe has a tendency to go towards a higher level of entropy. So basically, it's moving away from order and it's going towards more disorder. And why is that? Well, there's many reasons for this, but I can sum it up very quickly. Is that when you're thinking about order, order is unstable. Disorder is way more stable. So when you think of stable versus unstable, the odds are that anything will eventually go towards a more stable state. High order is unstable. Disorder is more stable. And in order to bring it back to this state here, we need energy. Okay, so in order to bring back a system from a disorganized state to an organized state of order, which is unstable, we will need to spend energy for this. So when we want to look at chemical and biochemical reactions, there are two types of reaction that can happen. Some reactions are known to be spontaneous, and what we mean by that is that they will happen almost immediately, almost by themselves. I say almost because that's not always the case, but almost. And there are non-spontaneous reactions that we need to force them to get into a certain state. So let's explore a very simple reaction here, which is the dissolution of sodium chloride, table salt. So this comes in crystals. I have salt in my shaker, and I add salt to a beaker full of water. What's going to happen is that this table salt here is going to dissolve and break down into its two components, which is an ion of sodium and an ion of chloride. This happens just like that. We don't need to do anything about that, right? This reaction here is known to be spontaneous. That happens without effort. We don't need to bring any energy in the system. It just happens. Okay? So that is an example of a spontaneous reaction. It just happens without, no energy. Unless the water is really, really cold, it's going to take more time, but it's still going to happen. Now, I'm going to bring another example, which is still a spontaneous reaction, but it is different in this case. So, if I have a gas, which is hydrogen gas, so the state here is gas state, right? And I mix this hydrogen with another gas, which is oxygen gas, and when those two gases meet, they can create a very explosive reaction, a very quick reaction, and they will form water. Okay? Water will be created. So this here is spontaneous. However, in order to get this reaction going, we need to nudge it a little bit. So if hydrogen and oxygen are mixed together and nothing else happens in a jar, well, nothing's going to happen. However, if I have a tiny spark in that jar, so say that I can generate some kind of a spark, just a tiny bit of energy, this reaction will go very, very quickly, and it will release a huge amount of energy. Okay? So energy will be created, will come out of that. And of course it will come out in flames, right? There will be an explosion. So in that case, the energy here is a lot of heat, right? Kinetic energy. So what we have here is two gases, but the most stable state for this or this, so if we look at this reaction, the reaction that is the most likely to happen when we have these two here, provided that we give a little bit of a nudge, is this here. Water is really, really stable, as we know. This here, not so much. So now let's look at a hypothetical non-spontaneous reaction. And I have two compounds here, A and B, and in this reaction, A and B combine to create compound C, right? So we have A, B, and then here we have a combination of A and B together. They are now linked together. So if we know that this is a non-spontaneous reaction, what it means is that this compound here is less stable than the two compounds together here. So this here has a higher energy, a higher level of energy than what we can find here. So this is more like disorder than this is. This is like more like ordered in a way. And of course this goes against what we know is that nature usually tends to go towards a state of more and more and more disorganization. So in order to have this here, we will need to bring energy in the mix, right? We will need to inject in a way, a certain amount of energy in order for this to happen. In biochemical reactions, this energy, the kind of energy the cell uses, we have seen this previously, and it's known to be ATP. So ATP will be transformed into ADP, but by doing so, will allow this reaction here. So something happens here that allows this reaction to go forward, and whatever happens here is using ATP in order to have this happen, in order to allow this reaction to proceed to completion, where we have A and B mixed together to create this molecule here, which is molecule C. So this here happens all the time in all of our cells. This, we generate non-spontaneous reactions all the time. We are growing, we build bones and muscles, and we can run, we can reconstruct. If you have a bone that's broken, it won't stay broken, it will heal, right? All of these things allow the cells to reconstruct. So reactions like this, non-spontaneous, doesn't mean they're not going to happen. It just means that they won't happen by themselves. So that's a very important thing to understand here. So at this point, I need to introduce the concept of activation energy. And that is a quite important concept in biochemistry and cell biology. So I'm going to draw a graph here, and I want you to really take it slow and understand what this graph is all about, okay? So what I'm going to draw here is the reaction we've seen previously. So where we have A plus B, and then A and B combine together and create this molecule C. And we know that this is a non-spontaneous reaction. So basically, we know that we will need to have a certain amount of energy injected in the mix so that this reaction is possible. Without energy, forget about it. This reaction is not going anywhere. Okay? So let's draw a graph here. Let's draw a graph where I have the energy level on that axis here. The energy level. And then what I have here is a scale of time. Okay? So chemical reactions happen within a time frame. They take their time. They might be very quick at our scale, but they need to happen in a certain sequence of events. And these sequence, these small events, put one after the other, they happen on a time scale. So time here, I'm not going to define it as hours or minutes or nanoseconds. It doesn't matter. What matters is the generic understanding of that graph here. So since we know that A plus B will combine to form C, and we know that C is at a higher energy level, right? It has a higher energy level because it is non-spontaneous. It's basically the same thing as putting a ball at the bottom of a stairs and waiting for the ball to go up the stairs. That's not going to happen by itself, right? Somebody needs to kick the ball up. We need to provide some kind of energy. However, if we have a ball at the top of the stairs and we push it just a tiny bit, the ball will come down just by itself, spontaneous, versus non-spontaneous for a ball going up the stairs, okay? This is important to keep that in mind. So what we know is that when we start the reaction, right, we have our two compounds right here, and we are at a certain low level of energy. So what we have here at this point in time right here is that we have A plus B together mixed in a beaker, for example. And this here, this level, is quite low, right? So we would have 0 here, and we would have like a scale of energy that's quite high as we go up this axis right here. So what we also know is that at the completion of this reaction, we have a higher level. So when we have C here, we are now at a higher level of energy, right? So if we compare C and A and B, we know that there is a difference in energy between this level here, which is at the end of the reaction, and this level here, which is at the start of the reaction. So we know that somewhere we are going to have a higher level of energy here, okay? So it would be so simple, right, if we had something like this. Okay, well, I just bring ATP in, and my ATP just mixes in, it adds, it's used, and then it turns into C, and there you go, you have a higher level, right? Why is it a higher level? Well, because ATP has lots of energy, higher level. Well, it doesn't work like that. There is something that we call activation and energy of activation, or activation energy. And this is what I want us to look at right now. So let me redraw this again, and then I have my compound C here. That's at the end of my reaction. And then when I follow this reaction over time, I can see that this energy goes like this. You see this here? What we have here is a little bump of energy, and it comes down a little bit. So what we have here is that this reactions, and most reaction, I would say like the vast majority of reaction, always need a little bump in order to proceed. And that little bump here is important. And as you can see here, you might think, wow, how is that possible? It's already difficult to bring it here. Why does it need to go this high here? Well, that's the energy of activation. We need to bring the compound at a certain level, A and B, at a higher level than where it is. We bring it together, and what's happening here is that we need to bring these two together. We need to bring A and B, A plus B. We need to bring them so close together to make them react and then get transformed into C. So that's what is different, is to bring those two compounds together and allow C to be formed. That's why we have this activation, this energy activation here, okay? So that's important. Now you might think, okay, well, you're telling us about a non-spontaneous reaction, so there's activation energy, okay. So activation energy is always required. We always see this when we have a non-spontaneous reaction, right? Well, actually, no, that's not true. You see this even for many spontaneous reactions. So now let's look at that as well. So the example I gave earlier was the mixing of two gases, right? So we looked at oxygen and hydrogen mixed together. We have the same graph. We have an energy in our time. And then what we do here is that we have oxygen and we have hydrogen that are, both of them are in gaseous states, right? So we have this here, they are together, and then we know that the molecule that is formed from this reaction, so if we have the reaction here, H2 plus O2 will give us H2O with a release of energy. This is a spontaneous reaction, right? So at the end, we have water that will be formed right here, right? And if you check here, the level of energy of water is much lower than what we have in those two gases here. Still, when we have a reaction, we still have this energy of activation right here. You see, there's a little bump of energy. So remember what I said, right? If we have two gases, those two gases mixed together in a beaker, right? So I put a little bit of oxygen and hydrogen, and I leave it like that. I'm very careful not to create any spark and not at too high a temperature. Nothing is going to happen. It's going to be like this. It's going to stay this way. But if I introduce a tiny spark in the mix, then we're going to have this here. We're going to have this compound here. What's going to happen is that the oxygen and hydrogen are going to get really close and start to exchange electrons and create a covalent bond that will create water. Once again, what we have here is the energy of activation. Okay? So this energy of activation can be provided. What is necessary for the reaction to go can be provided in many ways. In this case here, can be provided by heat. It can be provided by a spark, which is basically heat. It can be provided by light. It can be provided by kinetic energy even. But sometimes in biological systems, we cannot increase the heat. We cannot introduce a spark. We need something that will help us overcome this energy of activation. So you see, we need to bring, in order to go all the way down to water, we need to bring the system to a higher level of energy. Otherwise, the reaction will never take place. So what is this here? Well, what brings it up, in this case, is the spark. But in case of a cell, and what is it, right? It's ATP. Okay, right. That's good. Good. ATP. But how is ATP introduced? How does that work? ATP, how is this going to react with components to bring these components together? That's the next part that we're going to look at. So when we have non-spontaneous reactions, even sometimes spontaneous reactions, when we want these reactions to proceed and to go from one state to the other, which is bringing back the equation I had before, A plus B will give us C. And we know that this is non-spontaneous, so basically we need to bring energy in here, right? So what we want to do is we want to bring this reaction, we want this reaction to go ahead. So we start at a lower level, and we bring the reaction to a higher level, which is C forming. And we know that this reaction, when we look at the energy levels of the whole reaction according to time, it goes up at some point, and the difference between this here and this here is known as the energy, activation energy, or energy of activation. So what I want to show here is what happens at this very precise point. How is this possible? Okay? We cannot, like I mentioned before, we cannot, if we're studying cells, we cannot bring the temperature up so high for cells, because we know that cells will die. Cells will be destroyed by the amazing agitation of the water molecules in the mix. Proteins will be denatured and all of that. So that's for sure, that's absolutely never going to happen with just heat. So what we need is something else. We need something that will allow us to go through this bump, to go ahead past that bump in order to create C. And if we don't have anything to bring us to a higher level of energy, then this will not proceed. Okay? So what does that? How is this possible for cells to do this? Well, cells have tools that are called enzymes. Now, remember that enzymes are proteins. So basically, it's a protein with a very, very specific function. Okay? And let's say that the enzyme needed for this reaction to proceed here, let's say that we call this enzyme, let's say enzyme ABC, okay, for the reaction we need there. Okay, so let's call it enzyme ABC. Now, what I want to show is what is going to happen. How is enzyme ABC going to interact with AB in order to form C? That's my goal right here. Okay? So, what I want to show here is that we have our two molecules. So the first one kind of looked like that, right? So I had my molecule A here, and then I had my other molecule that was B, and that kind of looked like that. So what we want to do is bring those two molecules together and form this molecule right here. We have A and B, but then this will give us, this molecule is now called C. Okay? So this is what we want to look at right now. Well, what happens? And how do enzymes come in the mix, and how do they allow this to happen? Well, here's what's going to happen. When we have an enzyme, the enzyme is a protein that has a very specific function. And the enzyme, let's say this is our enzyme here. So let's say we have our enzyme right here. And we have a tube or a beaker in which we have A and we have B. We have A and B together with the enzyme. Our goal is to eventually create C. The enzyme, what it's going to do is that this enzyme here has a very specific spot in it that will allow our molecules to bind within the enzyme. Okay? So those two molecules, what I have here is A, and then I have B here. These two molecules will find a spot, a little nook inside that enzyme, this enzyme called ABC, and will be bound there. So the enzyme basically has a spot A, a spot for B, and a spot for A. And this enzyme here will lower the activation energy because it will use ATP. So ATP is going to be introduced in here and is going to interact with the enzyme. So ATP will be bound somewhere and the enzyme is going to connect with it. This ATP, as soon as the enzyme connects with it, this ATP will be transformed into ADP and it will release energy. That energy will allow the enzyme to change shape. And what it's going to do is this, right? So it will start like this, but after a while, and that happens very, very quickly, the enzyme will change shape and bring those two molecules very, very close together. They'll get closer and closer because ATP has released some of the energy and the protein can change shape. Proteins change shape all the time. So it will change shape and bring these two together. And once the enzyme, so that's our enzyme right here, once this enzyme has done that, once we have our final molecule like this, and this is our enzyme, once this enzyme has connected those two together, the enzyme is going to take off. Unchanged, ready for another reaction, and our molecule C right here is now going to be formed. So you see, what happened here is that the enzyme used the energy from ATP. Once the ATP got transformed into ADP, energy was released. Because of that energy release, the enzyme changed shape and brought those two pieces together, right? It brought those two pieces together and then clicked them. And then after that, left. And we were left with this piece here, C. So when we look at the energetics, the graph of this reaction, so remember that we have something like this, and we had A and B were here, and then C was here, and what we have here is a difference, the energy of activation right here. This is where the enzyme got the ATP from. This is where we have a bump here, and the enzyme allowed this to happen. And basically what it did is that instead of having this big mountain in front of you, because A and B don't react spontaneously, what the enzyme did is this. Graph again. So we have A and B, not reacted yet, right? Not reacted yet. C right here. C has a higher level. Reaction, energy of activation. Without E, this is what the energy of activation looks like. Now, when you throw in the mix, when you bring the enzyme, the activation energy is much lower. You see, this one here is with the enzyme. So the energy of activation is lowered. Why is that? Well, because the enzyme brought A and B together, used ATP to bring them even closer so that they could react and form C. So that's what enzymes do. So we cannot talk about enzymes without talking about something that's called the active site. Now remember one thing is that when you're thinking of enzymes, enzymes are proteins. Okay? Proteins are made of amino acids. Amino acids will get linked with one another and form the primary sequence, right? The primary structure. These amino acids will start to interact with one another and form the secondary structures. The secondary structures will start to interact with one another, forming the tertiary structures, and sometimes those tertiary structures will form subunits that allow some interactions between those subunits. So that's a quaternary structure. We don't need to get there right now, okay? But I just wanted to play this back just so that we keep this in the back of our heads, right? So what I want to bring now is the concept of what an active site is. So what we have here is we have our two molecules, right? So we have A and B, and our goal at the end will be to form something like this that is called C, right? So A and B reacts together to form C. Now we know an enzyme will need to be involved, okay? So let's look at this. Let's look at those two reactants. We know that they cannot interact by chance, just like that. We need the intervention of something that will allow the process to go through an activation energy that's quite high. It's quite a big mountain to go through in order to go on the other side. So the enzyme basically brings the mountain down a little bit, the energy down, so that the reaction can now proceed. So when we look at those two reactants, we know that they need to be brought together pretty close in order to interact and interconnect with one another. And we know an ATP will need to be involved in this case. Okay, now that we all know this, we all have this in our minds, now let's look at what's happening here. If I bring the enzyme, so we have A and B here, and if I bring the enzyme, and let me bring this just a little bit closer, it'll be easier. The enzyme will recognize those two molecules here. Now, when I say recognize, it's not that the enzyme is living or anything like that. The enzyme is just a stupid protein, okay? There's no thinking, there's no life whatsoever, okay? It's very useful, but it has evolved to be like this. Something living made this enzyme because it needed it. I'm not going to get into the evolution of things, at least not for now. So what I want to say is that the only enzyme that can do this reaction here is what we call enzyme ABC, right? So we know that enzyme ABC is the enzyme that's needed for that. And why do I say this? Well, one thing that I want to say is that enzymes are very specific to their substrates. Oh, new word. A and B right here, they're called substrates. So let me just write this underneath, substrates. So substrates are basically the building blocks of C. Okay, so the substrates are what is going to interact together to give something that's C. And C is the product. So when we see this here, that's our molecule C. Those two substrates will interact with one another and create this product. Okay, so it's a product of the enzyme reaction. Okay, this is what we have here. So, coming back to what I was saying, now that we know there are substrates and products. Perfect. What's going to happen is that enzyme A, B, and C is going to recognize those two molecules, right? So this is my enzyme here as I drew it before. So that's my enzyme right here. And the enzyme has a pocket for this substrate right here, right? Substrate B and substrate A. It has a pocket for both of them. It's built in. And when ATP comes in, this here is going to squeeze. This protein is going to change shape. And by changing shape, it will now create this molecule here. Okay? So we needed to change shape here. It's squeezed in a way. That site here, what happened here is of course, it's a chemical reaction, right? There's a covalent or more than one covalent bond that was created here. That site, the spot where this happened, is called the active site. So if I remove my product where my substrates were before they reacted, right? So this spot right here, is the active site. This here is the active site, okay? This active site is made of all the amino acids that happen to be in this region here, okay? And the amino acids here are always the same for enzyme A, B, C, that specific enzyme. If we have another reaction, say Y and Z reacting together, well, we'll need another enzyme for that. This enzyme here is no good for that. So that's an important part. So this here is called the active site. Once the reaction happens, our product, C, has no spot to stay, right? Because the enzyme has a spot for A and B, but it does not have a spot for C once C is formed. And in that case, C is ejected, and the enzyme can go on and do another reaction. So an enzyme is only a temporary passenger, right? It comes in. It's like as if you go to a party, you meet you're alone there, you don't know anybody. So somebody comes to you and say, hey, this is so and so. And so I present you Joe. This is Mary. Mary, this is Joe. You're both of my friends, but I need to go and do something so you can talk together, right? Mary and Joe maybe would never have talked, maybe would have never have met if it was not for the intervention of the host, right? The host is like the enzyme, and the two people are the substrates, okay? So, and then the enzyme can go on to do something else after, right? So that's what's important here. So don't forget active site, and don't forget the fact that the enzyme is specific to this reaction here, and only to this reaction here. Don't forget that in the active site, there is a spot for both substrate to fit, but then once they react, there's no spots for the product to stay in there. So that's why it doesn't interact anymore, and that's why it's ejected, right? So the enzyme can now move on to something else. So that's the important part about this.